Howdy. This video is on Lewis acid-base chemistry and metal complex formation. Lewis theory's acid-base is the most general acid-base theory that we've talked about. Lewis acid-base theory can be used to explain many chemical reactions, including metal complex chemistry and those in organic chemistry. Lewis acid-base reactions are common in biological systems. And so after watching this video, you should be able to describe Lewis acid-base theory. You should be able to determine if a compound is behaving like a Lewis acid or a Lewis base in a reaction. You should be able to describe the characteristics that make something a good Lewis acid or a good Lewis base. So we've talked about three acid-base theories. The Arrhenius theory is the simplest. It says if you add it to water, it produces hydrogen, then it makes it an acid. If you add it to water, it produces hydroxide ions. That means it must be a base. Bronsted-Lowry theory and Lewis theory are about in a reaction, how is it behaving? So according to Bronsted-Lowry theory, if in a reaction something donates a hydrogen, that makes it an acid. If in a reaction something accepts a hydrogen, that makes it a base. For Lewis theory, if something accepts an electron pair, that means it's an acid, behaving like an acid. If something's donating electron pairs, that means it's behaving like a base. Now Lewis theory and Bronsted-Lowry theory are consistent. All Bronsted-Lowry acids are Lewis acids, but because Lewis theory is a bit more general, not all Lewis acids are Bronsted-Lowry acids. And so it's kind of cool. We can look at this reaction, ammonia plus water, and we can describe it using Bronsted-Lowry theory or Lewis theory.
Ammonia is a base in the Bronsted sense because it acts as a proton acceptor. For example, it accepts a proton from a water molecule to form the ammonium ion and hydroxide ion.
And so looking at it in terms of Bronsted-Lowry theory, we look at the transfer of the hydrogen ion. The water is losing it, donating it, making it acid, and the ammonia is accepting the hydrogen ion, making it a base.
In the Lewis acid-base theory, the emphasis is on the electron pair. Ammonia is a base because it acts as an electron pair donor toward the proton. The proton is an acid because it acts as an electron pair acceptor.
And so if we look at the same exact reaction, but this time thinking about Lewis theory, we see the ammonia is donating electron pair, and so that's making it a base, and the water is accepting electron pair, making it an acid. And so again, same exact reaction. We just focus on different things depending on which theory that we're using. And so we go look at this reaction. Is ammonia behaving like a Bronsted acid, Bronsted base, Lewis acid, or Lewis base? And so what's happening is the ammonia is going to bond to the copper, and those bonding electrons are actually coming from the lone pair of ammonia. So the ammonia is donating electron pair, and so that makes the ammonia behaving like a Lewis base. Now we don't have any transfer of hydrogens, and so we cannot use Bronsted theory to talk about that top reaction. Now if we look at the second reaction, we see the ammonia again is going to donate its electron pair to grab that hydrogen, and so it's using its electron pair, it's donating it, so it's a Lewis base. It's grabbing the hydrogen, and so it's also a Bronsted base. And so for that second reaction, we can use Bronsted theory or we can use Lewis theory. And again, Bronsted and Lewis theories are consistent. It's just Lewis theory is more general. And so all Bronsted bases are Lewis bases, but not all Lewis bases behave like Bronsted bases. And so for Lewis acids, they accept electron pairs. We call them electrophilic. Often they'll be metal cations, and so they can accept the electrons. Or they can be an atom or ion or molecule with an incomplete octet, so like boron trifluoride or aluminum trifluoride. Molecules with a central atom that can have more than an octet, like silicon tetrafluoride. And so all these can be Lewis acids. They can accept electron pairs. Lewis bases donate electron pairs. They're nucleophilic. And so atoms or molecules with at least one lone pair of electrons make Lewis bases. And so if we look at this reaction, we have carbon dioxide plus water going to carbonic acid. And so the water is going to donate its electron pair. And so in this case, the water is actually going to behave like the Lewis base.
Dioxide acts as a Lewis acid toward water. One of the unshared electron pairs on oxygen is donated to the carbon atom, as one of the CO double bond electron pairs is moved onto the oxygen of carbon dioxide. A proton from the water molecule moves to the oxygen of the carbon dioxide molecule, completing the formation of carbonic acid.
This is kind of interesting. So carbon dioxide is in the air, and it can get absorbed into water. And so natural waters typically have a pH lower than 7. They're slightly acidic, in part because of the carbonic acid formed by the absorption of the carbon dioxide. And so here we have ammonia. Again, it's going to donate its electron pair. And so it's going to behave like a Lewis base. Again, there's no transfer of hydrogen, so we cannot use Bronsted theory for that top reaction.
Lewis acid-base theory is more general than Bronsted theory because it applies to systems that do not involve protons. For example, ammonia acts as an electron pair donor toward boron trifluoride, a molecule that has a vacant 2p orbital.
Now again, here's a metal complex. And so the bond here is formed from the lone pair of the ammonia. So the ammonias donate the electron pair, forming that bond. And so again, the ammonia is behaving like a Lewis base. The metal ion is accepting the electron pair, so it's behaving like a Lewis acid.
Ammonia also acts as a Lewis base toward metal ions, as in this example of the cobalt-3 hexamine complex. The ammonia electron pairs are donated into vacant metal orbitals.
And so metal complexes are fairly important in many applications. Porphyrin are naturally occurring polydentate ligands. And so poly meaning many, dentate bite. And so for porphyrins, they can actually form multiple bonds with a metal ion. And so you can imagine that, say, these hydrogen aren't there, you could have a metal ion in the middle and actually have 4 bonds with the porphyrin. Hemoglobin contains 4 different porphyrin groups. And again, this is how oxygen is carried in your blood. It's also kind of interesting. For chlorophyll, it also has a porphyrin group, but instead of iron in the center, it actually has magnesium in the center. And I think there actually should be 4 bonds to that magnesium. And so oxygen is carried through in the blood with the hemoglobin using the porphyrin group with the iron. Unfortunately, the iron can couple to the oxygen or can also bond to the carbon monoxide. Now, the carbon monoxide is actually a stronger Lewis base than the oxygen, and so the carbon monoxide will bind preferentially to the iron.
Oxygen binds weakly to the iron ion at the center of a heme group in the hemoglobin molecule. In an oxygen-poor area of the body, the O2 is easily removed. Carbon monoxide, in contrast, binds very tightly to the iron and is very difficult to remove. The presence of carbon monoxide makes it impossible for the blood to transport oxygen effectively.
And so here's some interesting chemistry. So we have copper sulfate. We're starting with it. That gives us the blue. Now if we add ammonia, the ammonia will react with the water, forming the ammonium ion and hydroxide ion. Now the copper will then bind with the hydroxide to form copper hydroxide solid. Now if we add more ammonia, the ammonia will actually form a complex with the copper ion.
In the test tube is a solution of copper sulfate. When we add a few drops of ammonia, the ammonia acts as a Bronsted base and causes the precipitation of solid copper-2 hydroxide. The solution turns a cloudy blue. If we then add a much larger amount of ammonia, the solution turns a very dark blue. The precipitate dissolves upon direct reaction with ammonia molecules. The ammonia has donated its electrons to the copper ion, and so now acts as a Lewis base.
And so in this first reaction, ammonia plus water going to ammonium ion plus hydroxide, again, you can use either Bronsted-Lowry theory or Lewis theory. In terms of Bronsted-Lowry theory, we'd say the water is donating its hydrogen ion to the ammonia. In terms of Lewis theory, we'd say the ammonia is using its electron pair to grab the hydrogen ion. And so in this reaction, ammonia is behaving like a Bronsted base and a Lewis base. Water is behaving like a Bronsted acid and a Lewis acid. Now, in this reaction where we have the copper hydroxide plus ammonia, we can't use Bronsted theory because there's no transfer of hydrogen ions. But we do have ammonia using its lone pair to form a bond with the copper. And so the ammonia is behaving like a Lewis base here, and the copper ion is behaving like a Lewis acid.
Ammonia is a Bronsted base and produces hydroxide ion in solution that can lead to formation of solid copper 2 hydroxide. With additional ammonia, a Lewis acid-base reaction occurs.
And so a reaction of a metal ion with the ligand forming the metal complex, the Ekman constant is going to be a Kf, a formation constant. So just like we had Kas where we have acids dissociating, or Kbs for basis association, for formation constant we cannot use what's referred to as a Kf. And so for a Kf we have a metal ion plus a ligand going to the metal complex. Now if we flip it, so take the products, fragments, reactants, reactants to products, remember the new Ekman constant is going to be 1 over the old Ekman constant. And so just like for polyprotic acids where we had a Ka1, Ka2, Ka3, for formation constants we can also have a Kf1, Kf2, Kf3, Kf4. Now also for the acid example, Ka1 was always greater than Ka2, which is always greater than Ka3. We see the same thing here. Kf1 is always greater than Kf2, which is always greater than Kf3. And so the 1 means the first ligand is binding to the metal. Kf2 means that the second ligand is binding to the metal. And so here's a table. We have Kf1 through Kf6, and we have 6 different metal ions, and then these are the values for those Kfs. Now we could be asked a question like, what is the Ekman constant for the following? And often when we see that, we have to figure out, okay, what reactions can we add to get the reaction that we're looking at? And so we see we have a cobalt phosphate plus ammonia going to cobalt ammonium. This is a metal complex plus phosphate ion. And so what we could think about would be, say, the solubility of cobalt phosphate. So that would be a KSP. And we could think about the complex formation for this cobalt ammonia complex. Now the Ekman constant for this top reaction is just KSP, and for this one it's going to be Kf1 times Kf2 because we're adding 2 of those ligands, and because the reaction was multiplied by 3, it's going to be to the power of 3. And so the Ekman constant for that top reaction is just going to be 6.3 times 10 to minus 2. Now notice when you add these 2 reactions, you multiply the corresponding Ekman constants. And also notice that when you add these 2 reactions, the cobalt ions actually cancel. And so according to Le Chatelier's principle, should cobalt phosphate be more soluble in pure water or a solution that contains ammonia? Well, if you think about Le Chatelier's principle, by adding the ammonia, it's consuming this cobalt ion, and so it's pushing this reaction to the right. And so based on Le Chatelier's principle, we'd say that the solution of this cobalt phosphate should be more soluble in a solution that contains ammonia than the one that does not. We could also ask, according to the values of the Ekman constant, should cobalt phosphate be more soluble in pure water or a solution that contains ammonia? And so it's, again, it's going to be a solution that contains ammonia. If we look at it, the KSP of cobalt phosphate in pure water is 2.05 times 10 minus 35. The Ekman constant for this reaction, which is cobalt phosphate in a aqueous solution that contains ammonia, is 6.3 times 10 to minus 25. So this one's much larger. It's 10 orders of magnitude larger than pure water. And so we say it should be more soluble in a solution that contains ammonia. Again, we can think about it in terms of Ekman constants. We can also think about it in terms of Chatelier's principle. And so there's a lot of different metal complexes. This is one with copper and ammonia. And again, the ligands are behaving like Lewis bases. They're donating electron pairs. And so there's neutral ligands, like a water, ammonia, NO, CO. This is ethylene diamine. This is diethyl triamine. You can also have anionic ligands. Anionic just means it has a negative charge. And so you could have just fluoride ion, chloride ion, bromide ion, etc. You can also have some polyatomic anions. And again, if you look at the Lewis diagram, we see that all these have a lone pair. And again, they need that lone pair so they can donate the lone pair so they behave like a Lewis base. Now the coordination number is the number of attached donor atoms to the metal complex, to the metal atom. And so coordination numbers are often 2, 4, and 6. And so if you have coordination number 4, you can have a tetrahedral shape, or you can actually have a square planar shape. The square planar is typically for transition metals with 8d electrons. And so this is the tetrahedral shape, and this is the square planar. This molecule is kind of interesting. This is referred to as cisplatin. It's actually used as an anti-cancer drug. It's kind of interesting if you move this amine down one so that the amines are across from each other. I don't think it has any medicinal properties. Coordination number 6, that gives us an octahedral shape. And so here we have 6 different ammonia groups attached to the cobalt. It's also kind of interesting. You can have a coordination number 6 and three ligands if each ligand binds to the metal in 2 places. And so the ligand here is ethylene diamine, and it's got 2 nitrogens. Each of these nitrogen has a lone pair, which is able to form a bond with the metal. And so 1, 2, 3 ligands, but it's bound to it in 6 different places. And so it still would be a coordination number 6. Now, polydentate ligands are called chelating agents. They appear to grasp a metal between multiple donor atoms. And so bidentate, bi is 2, so you have 2 bites ligands. So ligands that can attach to the metal in 2 different places. So ethylene diamine, these 2 nitrogens, the carbon ion, these 2 oxygen, the oxalate ion, those 2 oxygen. It's also kind of interesting, you can have some polydentate ligands that can do, say, 6 different places. And so this is EDTA. And so it can attach to the metal 1, 2, 3, 4, 5, 6 from 6 different places. And it can actually basically wrap around the metal. And so you can see the metal is that black sphere right here, and then around it is the EDTA ligand. And so I think it's been used to actually try to get toxic metals out of people's body. By chelating the metals, it's easier to excrete for the body. And so Lewis acids, they accept electron pairs. They're electrophilic, so they could be metal cations. They could be molecules with incomplete octet. They could be molecules that can have more than an octet. Lewis bases, they don't electron pairs. They have to have a lone pair to donate. Lewis acid-base chemistry, again, more general than Bronsted. You can think about complex formation using Lewis acid-base chemistry. I hope that was helpful.